Right. The topic for now is optical isomerism. What is optical isomerism? It is again under stereoisomerism. Stereoisomerism divided into two categories, conformational and configurational. Under configurational we have two categories, one is geometrical, the other is optical. Now in this topic we are going to speak about optical isomerism. So what is optical isomerism? If we look at so many day-to-day compounds that we are using a particular type of compound with a specific action. An example of this would be season of flu. Everybody uses cetirizine as a tablet for cold. That cetirizines complete name that you are using is levocetirizine. So what is that word levo? It indicates a particular optical isomer. So what does this example say? You have been using so many compounds which are part of this topic with much knowledge, without much knowledge about it. So what is that optical isomerism, or what is the importance of that word levo? We are going to see now. So scientists, they keep on experimenting, they keep on searching for different things. So in this process, they started passing some compounds through light and tried to analyze what is happening when light is passed through certain compounds. So instead of passing a direct light, they have taken a plane polarized light. What is a plane polarized light? Just I try to explain through this diagram. So plane polarized light is like this. So suppose this is the source of light. When you take a source of light, it gives light waves which are propagating in all the directions. If the light wave is propagating in all the directions, so the electric field vectors of the light waves you can represent in all the directions. Suppose this is the propagation and you are looking, this is the direction of the wave. The electric field vectors, that is light wave, is propagating in all the directions. That is what I am representing in this diagram. When you take this light which is propagating in all the direction and pass through a chemical solution, you will again get light which is propagating in all the directions. So there is no change. So it does not give any visible result. So instead of this light, what we are doing is we are taking a light and passing it through Nicol prism. Nicol prism is a material, or you can say we are passing through calcite crystals. So when you are passing it through Nicol prism or calcite crystal, the light gets filtered. This is filtering of light. You all know about this films that we apply on the car. That is, it filters off some amount of light. So that light that we are filtering off is in a way filtered through what you can say, a different polarizing material. One of such polarizing material is Nicol prism. Pause it. So when light passes through this Nicol prism, instead of propagating in all the directions, it propagates only through one direction. So just to repeat the statement, light waves are propagating in all the directions. That is, the electric field vectors, the component of the light is in all the directions, represented in all the directions. When it passes through a Nicol prism or a calcite crystal, what happens is the component now is propagating in only one direction. So such a light, which I can represent by this, where arrow is only in one single direction, not in all the directions, is called as plane polarized light. So we are going to use plane polarized light to analyze the compound. Earlier we tried with normal light, but now we are going to use plane polarized light. The plane polarized light is passed through a tube. This tube is called as polarimeter tube. What is there in the tube? A chemical compound is there. That sample chemical which I am going to analyze. Let us say the sample chemical is cetirizine. That is an organic molecule. So it is in the form of a solution. Keep that in mind. Now the light is passed. If there is no compound, as it is, the light would come out. But since the light hits the compound, there is some deviation in the light. Previously the light rays are coming like this. The propagation of the light is in this direction. Now because it is encountering the molecule in its path, it is the propagation of the light is in this direction rather than in this direction. Are you understanding the difference? Previously it is in this direction. Now you are viewing from that direction. It is in this direction rather than in this direction. So there is some change in the angle of light. So that change is what I am representing here. Just because it is passing through the prism, there is some change. So it is bent at an angle theta. That theta is the angle of rotation of light. That is an important word. What is theta? It is the angle of rotation of light. And observing from this direction. Now you are the observer. Light was initially coming like this. Now it has changed its angle in this direction. If the light changes its angle to the left, then it is levorotatory. Then you will classify the molecule as levo, that molecule. I have taken the molecule to be cetirizine. Now you will classify it as levocetirizine. If the light is bent to the right after passing through the polarimeter tube, I will call it as dextro compound. If it bends to the right, then I have to call the molecule dextrocetirizine. Now understand that right and left are just conventions. This side it is right to me, for you it is left because you are the observer. Okay, right and left are just conventions, but from the observer point of view, that is from the analyzer, after passing through the analyzer, we are saying levo or dextro. So just the view of the analyzer here. Initial light, which is represented in white color, after rotation, now it is at an angle theta to the right, it is dextro, represented by D or plus sign. If it moves to the left, the angle of rotation, angle can be same. Angle of rotation, if it moves to the left, it is L minus or levorotatory. If there is no rotation after passing through the molecule, such a case is also possible. All molecules do not respond to plane polarized light. Only some molecules respond to plane polarized light. If there is no change in the propagation of the light even after passing through the molecule, then it falls under the category of optically inactive. So we have three categories: dextrorotatory, levorotatory, and optically inactive compounds. This is about plane polarized light passing through molecules and optical activity. Rotation means optical activity. No rotation means optically inactive. Moving ahead, now what are optical isomers? Optical isomers have same molecular formula. For example, I have taken cetirizine. Molecular formula is same, but connectivity is anyway same because they are not structural isomers. But the configuration is different because I said they fall under the category of configurational isomers. Configuration means some orientation in the space is different. Configurational isomers. But what is the point of difference for optical isomers? They differ in the behavior with plane polarized light. That is how they rotate plane polarized light. If one molecule rotates, other molecule does not rotate, still you may call them optical isomers because there is change in the optical activity with respect to each other. One rotates positive side, other rotates negative side, still you may call them optical isomers. One rotates by theta, other rotates by minus theta. One rotates by theta, other rotates by, let us say, some alpha. They need not be equal, they can be different values also. That's enough, you can call them as optical isomers. This is the intro to optical isomerism.